So if we did go ahead and compute the equilibrium points, remember for a system that means dx dt and dy dt are simultaneously 0, and we solve for both x and y, so we actually get 4 equilibrium points. And if you notice the very first one, which is the equilibrium point 0, 3, that was the point that we were seeing some of these solutions converge to. So 0, 3 was like this guy right around here. That point 0, 3 is where some of the solutions were going. And for this other guy here, 2, 0, it also looked like some of the solutions were going to that point, 2, 0. And 2, 0 was this point right over here somewhere, right about there. That's the position 2, 0. So when x is 2, y is 0, when there are 2, whatever, million zombies or 2 units of zombies and 0 units of werewolves, there will be no change in either population. When there are 0 zombies and 3 werewolves, there will be no change in either population. When they're both at 1, they seem to coexist happily, and they both stay out that population size. And of course, when they're both at 0, that makes sense. In this case, 0, 0 is an equilibrium point, because if there's an absence of both predators, then there is not going to be any growth, unfortunately. Or fortunately, depending on how you want to look at it. So if we look back at the phase plane, we see that some trajectories end up at some of the equilibrium points. There must be some explanation. If we zoom in to look locally in the neighborhood of these equilibrium points, we might see something familiar. So let's just focus on 0, 3 and 2, 0 for a moment. Go back to the phase plane. So for 0, 3, I want to set my y value to be right around 3. So I'm going to go from about 2.99 on my y-axis to about 3.01. And then I'm going to, for x, be right around 0. So negative 0.01, so just slightly to the left of 0, to 0.01, slightly to the right of 0. And what I notice right in the center, where I have the point 0.3 right around here, is that look what happens to these trajectories. These trajectories, we seem to have some sort of straight line solution here, and it looks like another straight line solution here. You can see the arrows pointing directly inwards, and along this straight line they're also pointing directly inwards. So we might want to begin classifying this and thinking about this as a linear system. This looks a whole lot like a sink. This point 0.3 looks a whole lot like a sink. And if we look at right around the next coordinate, or the next point, and changing this right around to the point 2, 0, so I'm going to have my x value go from a little bit less than x equals 2, 1.99, to about 2.01. And this, we want y to be at 0, so let's go negative 0.01 up to 0.01 and see what happens. And boy, oh boy, it looks like this also seems to act like a sink. And in fact, if we start to look at these different trajectories, we see that all of the solutions seem to curve into the point 2, 0, the ones that are at least local to it. So the reason we're looking at just a small projection on either side is because we're only going to make an argument that this equilibrium point behaves like a linear system whenever you are within the neighborhood. Okay, so it's sort of like if somebody's having a loud party and they're blasting music, you're not going to be able to hear that music if you're 4, 5, 6 blocks away. I'm assuming it's not that loud, but as soon as you get to within that neighborhood, you know, a couple doors down, you're going to be able to hear it, right? And then you get super close to the house that's having the party, you're really going to be able to hear it. So we're doing kind of that analogy here, where as long as we're really looking at a region very, very close to the equilibrium point, then locally we're going to make the argument that that equilibrium point behaves like one of our linear systems. And so again, we see that here's a straight line solution, in this case along the x-axis, and the other straight line solution seems to be going at a diagonal. And this also looks like all the arrows are pointing inwards, so we'd classify this as a sink as well. We had another equilibrium point right at 1, 1, so let's also look within the neighborhood of the point 1, 1. So remember, neighborhood just means slightly to the left, slightly to the right. So 0.99 to say 1.01. And then we'll do the same thing here. We'll go from 0.99 to 1.01. And wow, doesn't that look a lot like a linear system? In this case, it looks like a saddle. We see that there appears to be a straight line going from diagonal bottom left to top right, as well as from top left to bottom right. And it looks like here the vectors are pointing inwards towards the equilibrium point 1, 1. But here along this straight line, they're pointing outwards. So it appears that the equilibrium point 1, 1 is going to be a saddle. And again, we're just within the neighborhood. As soon as we start to zoom out more and more, we start to see that very chaotic and unpredictable behavior that we saw in the original phase plane. But this begs an interesting question. How do we mathematically quantify each of the equilibrium points in the event that we couldn't look at them all, or perhaps in the event that we had more than 2 differential equations and we maybe had a system of 3 differential equations? It'd be a lot harder to try to look at all the equilibrium points in 3 dimensions. So we have a theorem for this that's called the linearization theorem, and we'll take a look at that in a moment. And just some remarks here before we introduce the theorem. This was our original equilibrium point 0,3 that we looked at, and I've just sort of superimposed the 2 straight lines that represent the eigenvectors for the linear system right around that point. And we see that that is looks like a sink for a linear system. This was our where we were looking at the point x equals 2, y equals 0 right there. And we again kind of saw that there was a straight line solution there. Let me change colors here, make that black. So we see how that was a straight line solution about there, and that there's also a straight line solution along the diagonal right about there. We'll call that good. There we go. And so we again saw that in this circumstance, it appeared that all along the straight line solutions, all the vectors point inwards. And so that point right there, which is 2, 0, 2, 0, looks like a sink as well. Here is right around the point 1, 1. So 1, 1 is right inside of there. This one looked like a saddle. And so let me go ahead and kind of sketch in those straight line solutions from the linear system. There's one right about there. I know that's not perfect, but good enough. And so we see that the vectors point in on this straight line solution here, but they point outwards here. And so this equilibrium point at 1, 1, 1, 1 looks like a saddle point. Okay, and again, what we mean here is locally. Locally, within the neighborhood. It's only whenever you look at the phase plane very, very close surrounding that equilibrium point that we observe this happening. Because remember, when we zoom out, we see this. And you wouldn't be able to tell based upon this that what's going on near 0, 3 and 2, 0. But as we begin to zoom in and drive into that neighborhood, we can hear the music. We can hear the sounds of this particular behavior. I've also taken the liberty here to plot the point 0, 0, the equilibrium point, which is, you can see we have 2 straight line solutions in this case once again, and all of those vectors point outwards. So along here, they point outwards. And also, one of the interesting things to note is that none of our trajectories that we just sort of clicked in the phase plane on ever went to 1, 1. Well, that makes sense because 1, 1, it acts as sort of an attractor and repeller at the same time. So some solutions will near 1, 1, but they'll never actually get to 1, 1 because the vectors immediately push it away, the ones that are pointing outwards. In this case, we can never get to 0, 0 unless we start off at 0, 0 because all of the trajectories will kick it away. So 0, 0 acts like a repeller, which is why we didn't see any of the trajectories move to 0, 0. And remember, this looks like a source. Once again, we want to say locally because we zoom out, we don't see that anymore. Perfect. So we've kind of visually classified these, and I'll say locally here as well. We've visually classified all of these, but again, we want to have some mathematical way to do it because mathematics gives us more of an objective viewpoint from which to take a look.